Time to look at another exam. This is going to be for Calculus 1, and also known as Math 165. It's our second exam, so we're getting a little bit more into derivatives, a little bit more interesting things that we can do with derivatives, maybe some applications, some fancier rules. So it's going to be a lot of fun. As always, if we're going to take this test, we want to get credit, we make sure to write our name, because only then will we know that we'll get the points. All right, let's begin. Number 1, we're asked to find the absolute minimum and absolute maximum values of a function f of x, which is minus 2x cubed plus 9x squared plus 24x, on the interval from -2 to +2. Okay, absolute, max, and min, absolute. And so, how does this one go? Well, this one is a fun one, because there's a song for it. And the song goes, we're making a list, checking it twice, gonna find out which points are nice, find the absolute max and min. That's right, we're making a list. Okay, so what do we mean? Well, essentially we're making a list of where all of the x values where we might actually attain the absolute max and min. Now, the first points we throw in our list, they're the easiest ones, and we always remember to put them in, are the endpoints. So in this case, -2 and +2. All right, the other places are a little bit more subtle. So the endpoints we could attain, or it might be somewhere in the middle. Now, we don't want to test every point because there's infinitely many points in the middle. So what we'll do is we'll say, okay, let's use our tools of calculus. And, well, our tools of calculus say, hey, if I'm an absolute max or min, I should be a local max or min. So I'm going to search for local max or mins. And we do that by looking for critical points. Now, this will be where the derivative is either 0 or undefined. So let's first look at our derivative and see what we have. So term by term, derivative of minus 2x cubed, that's minus 6x squared. Derivative of 9x squared, 18x. Derivative of 24x, 24. Now, some good news. This is never undefined. It's a beautiful function, polynomial. It's the kind of function we'd love to take home and meet our family. All right, so let's delve into it a little bit. And notice everything here is a factor of 6. It's almost like they wanted all these factors of 6 here. So we're going to pull that out. Minus 6 and x squared. If you pull out minus 6 out of positive 18, you'll have minus 3. Be careful. Be careful. Follow your signs. So you can check, right? Minus 6 times minus 3 is plus 18. Pull out minus 6 out of 24, minus 4. Okay, now does this factor? I suspect it might. All right, so minus 6. So I'm guessing it'll factor. Let's see, what do we need? We need two things that would multiply together to give us -4, right? Because we have that -4. But when we added them, we got -3. I can think of two numbers that do that. X minus 4, x plus 1, right? Because you see x squared, good. And the plus x minus 4x is minus 3x, great. And minus 4. Nice! Okay, so we have the derivative. There's no place where it's undefined. And we say, well, when does it equal 0? And this equals 0. You know, that's our question. Well, it's either when x equals 4 or x equals -1. All right, now, which of these goes on our list? The answer is -1. Okay, so let's put that on, and then let's talk about it. Why -1 and not 4? So remember, we are looking for x values between -2 and +2. And so, when we're looking for points, we only care about -2 and +2. We don't care what happens on the outside. 4 is not between -2 and +2. It's on the outside. So it's like, I don't care what you're doing. You're a distraction. You're there to maybe mislead us, trick us into thinking we should pay attention to you, but we know that we will not. Okay, so that says we only need -1 because that's in our interval. And now our list is complete. Now, we're not done with the question. What does the list represent? The list says this is where it could occur. And so we say, okay, now that we know where it could occur, we need to plug in. So in other words, these are our x values, and we're going to plug each one of these into our function. Okay, and this is probably going to be the tricky part here, because we actually have to plug these numbers in. So let's just do it carefully. We'll start with f of -2. So that's -2 times -2 cubed plus 9 times -2 squared plus 24 times -2. Now, -2 cubed will be -8. And there's another -2. This makes it 16. -2 squared is 4 times 9 makes 36. And 24 times -2 is 48. So 16 and 36 added together, 52. Subtract 48, we get 4. Okay, so that's 4. All right, now f of 2. Well, that's -2 times 2 cubed plus 9 times 2 squared plus 24 times 2. Well, -2 times 2 cubed, well, 2 cubed is 8 times -2 is -16. 9 times 2 squared is still 9 times 4, which is 36. And 24 times 2 is 48. Now, if we add -16 and 36, what happens is we get 20. Add 20 to 48, we get 68. All right, well, that's a pretty good number there, 68. Okay, one more point to check. F of -1. Okay, so that's -2 times -1 cubed plus 9 times -1 squared plus 24 times -1. Okay, so -1 cubed is -1 times -2 makes a +2. -1 squared is 1 times 9 makes 9. 24 times -1 makes a -24. So we have 2 plus 9, which is 11. Then we're subtracting 24. And 11 subtract 24 is -13. If you like, think of it the other way. What if I asked you for 24 subtract 11? You're like, oh, 13, right? Well, that's the negative of our answer, right? We just flipped the sign and everything. Okay, so -13. And we're ready to write down our answer. In fact, it's basically done. What's left? Well, let's recall what the problem was asking. It says find the absolute minimum and absolute maximum values of our function on this interval. So we made our list, we plugged each point on our list into our function, and now here's the great thing. The biggest number is the biggest number. It's the absolute max. So 68, that's our absolute max. And our smallest number, which is -13, that's our absolute min. And so there we are. Our absolute max is 68. Our absolute min is -13. We should just double check to make sure it didn't ask where did these values get achieved, and it doesn't ask that. We just need the values themselves. And so there we are. We're done. Woohoo! Ah, what a nice way to start. Let's keep going. Number 2. Use logarithmic differentiation to compute the derivative of, well, we have y is 2 plus cosine of x times e to the arctangent of x over root 1 plus x. And it says no credit will be given for other differentiation methods. And your answer should be a function of x alone. Do not simplify your answer. Wow. Okay. Now, we should note before we start, technically you don't have to use logarithmic differentiation to do this problem. Why? Well, logarithmic differentiation is an absolute must if you see a function raised to a function, you know, x to the power x, something like that. It's hopeless without logarithmic differentiation. We don't have that. But what we do have is lots of sort of messiness, lots of multiplying, dividing, exponentiation. These are wonderful things to apply logarithmic differentiation to, because logarithms are great ways to simplify multiplication, division, things to powers, you know, exponentiation. And so we're going to follow what the problem says. Because of course, what do we want? Credit. And it says no credit if we don't do it, so we're going to definitely do it. Okay, so we should probably start by reminding ourselves what is logarithmic differentiation. Now there's a couple of ways to write this down, and I'm going to write down how I think of logarithmic differentiation. Other people have different ways, and that's okay. That's okay. So here we go. So if I want to find the derivative f prime of x, I claim that this is equal to, okay, so we said this was the derivative of f of x. All right, that's just another way of saying this. This is f of x times the derivative of natural log of f of x. And that's it. This is logarithmic differentiation. Okay, why is it true? Well, you can check that it's true by just carrying out the differential here. Here we have a function f of x inside the log function. What we would have is the derivative of the inside, well, first off, sorry, not derivative of the inside, I'm getting ahead of myself. Derivative of the outside, plug the inside in. Derivative of log is 1 over. So 1 over f of x times derivative of the inside, and then what happens is the f of x's cancel, and we get what we want. So that's why it works. So why do we call it logarithmic differentiation? Well, spoiler alert, it has a log. All right, so what do we do? Well, we're after our derivative, so it says, okay, so our derivative will be our original function, 2 plus cosine of x, e to the arctangent of x. I like this problem. It has an arctangent. Well, maybe I should say I like the aspect of this problem, the one that has an arctangent. Now we're going to multiply by the derivative of the natural log of all of this. All right. And I think maybe the hardest part of this problem is going to be writing everything down, because there's a lot to write down. Let's go ahead and write this square root of 1 plus x in a calculus-friendly way. So calculus-friendly means 1 plus x to the 1/2 power. Okay. Now, the reason we do all of this is instead of taking this derivative right away, we're going to simplify it, which means we're going to pull it apart, use the properties of logs. So maybe let's pause for a second. Okay, there we go. That was a good second. And let's talk about the 3 things about logs which are really cool. And we'll put it up here for reference. So nice property 1 is if I have log of a times b, that becomes log of a plus log of b. Property 2, if I have division a over b, that's log a subtract log b. So in other words, multiplication becomes addition, division, subtraction. And our last fun property, log of a to the b power, this becomes b log of a. All right, so exponents come down in front. So we're going to use all of those rules. And we can do it in one step, but if you're squeamish and you want to do a couple of steps, that's cool too. Maybe let's do a couple of steps just to help highlight things. So step number 1 that I'm going to take, so I'm not forgetting about this part in front, and I haven't forgotten about the derivative, is I'm going to basically use these 2 facts. Multiplication, division, it comes addition and subtraction. So this becomes 3 pieces because we have 1, 2, 3 pieces. The stuff upstairs is added. So log 2 plus cosine x plus log e arctangent x. And the stuff downstairs, subtracted. Subtract log of 1 plus x to the half. Okay. Now we're going to do another round, which is using this rule. And I'm going to use one more fact. You know, who doesn't love more facts? Log of e is 1. It is the 1. Okay, so 2 plus cosine of x e arctangent of x over square root 1 plus x, and times the derivative of, here there's nothing we can do. You cannot use logs to simplify because of that pesky add. Logs do not work well with addition inside the log. It works great with multiplication in the inside, but not with addition. So be careful. Don't be creative and create new rules, because they're probably not really rules. They're points waiting to disappear. We don't want that to happen. All right, now here, see we have something to a power, e to arctangent, a to b. All right, great. So what we can do is we can pull the arctangent down. So we have arctangent of x, and then we could think of it as log of e. But what's log of e? It's 1. So actually we just don't even write it. Okay, and then here, minus, again, 1 plus x to the half. 1 plus x to the half. So that becomes a half log 1 plus x. Cool, 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 cool. Now, at this point, you're like, great, we're done, right? No, why not? We haven't done any derivatives. Wait, what? We haven't? Oh yeah, you're right, we haven't. A lot of the work of logarithmic differentiation is not the differentiation step, it's the preparation step. It's knowing the rule, applying properties of logs to, pull things apart, and now our great, denouement. What have we been building up to? Okay, so here we go. We're ready to write our last step, which is our answer, because remember, we don't want to simplify it after we write our answer. So we still have, whenever you do logarithmic differentiation, that's a hard word to say for me right now, logarithmic differentiation. Whenever you're doing that, you're always going to have what you started with in the front. And that's okay. No worries there. And the only pesky thing is that we've had to write it a lot. Okay, term by term. Now, when you're taking the derivative of log, there's an easy way to do it. You make a fraction. You say, okay, what's inside the log? That goes downstairs. Oh, well, it's 2 plus cosine of x. Okay, and now take this term downstairs and take the derivative of it, and that goes upstairs. Well, derivative of 2 is 0. Derivative of cosine is negative sine. Now, what we are doing here, this is called chain rule. Right? Derivative of log is 1 over, so it's 1 over the inside, and then times the derivative of the inside, and so the derivative of the inside goes upstairs. Arctangent x, notice there's no log here. That's just a classic, beautiful 1 over 1 plus x squared. Gotta love arctangent. Beautiful derivative. It still brings a tear to my eye. Decades after seeing this, it brings me joy. If I ever have to go through my mind and say, okay, what formulas bring me joy that I need to keep? The arctangent brings me joy. All right, derivative of log, again, whatever it is on the inside goes downstairs, and times the derivative of the inside upstairs. So derivative of 1 plus x is 1. And that's it. We're done. Yay! And a great huzzah rose throughout the land. Huzzah! Huzzah! All right, so there we go. There's logarithmic differentiation. Now, I will say that there's another way that people sometimes do logarithmic differentiation, And so I'll quickly talk about what that idea is. Ultimately, it's the same. Namely, you say, okay, suppose you have y equals f of x. You say, well, take the log of both sides. So log of y is log of f of x. And now you take the derivative of both sides. Well, here you'd have 1 over y, y prime. And here, well, you'd have, well, let's just say the derivative of the natural log of f of x. And now you say, well, I don't want y. So you say, well, wait, I know what y is. This is really 1 over f of x. And you say, oh, well, great. So I'm going to move it across and come to the conclusion that y prime is f of x times the derivative of the natural log of f of x. And you say, okay, so the process is take log of both sides, take derivative, remember to get it back in terms of f of x, move it across. Well, do you recognize that formula? It's right there. So whatever helps you, that's the way you should do it. All right, but that means we're done with number 2. Off to number 3. Number 3. Let f of x have inverse function f inverse of x. Okay, sounds reasonable. And let f of x have derivative function f prime of x. Okay, that also sounds pretty reasonable. Suppose that we know the following information. So we don't have a formula for the function, but we have some information about the value of the function at some various points. All right, so it looks like we're going to be doing a lot of table reading here, but that's all right. So here we go. Part A, find f of 2. So f of 2 says we plug 2 into our function. And so this is our input 2. So f of 2 would be 3, right? We plug in 2 into f, we get 3. So f of 2 equals 3. All right, good, good. And f inverse of 2. Okay, now f inverse of 2 is interesting. What does that mean? It says we want the output of f to be 2. So now, see, previously we said our input is 2. All right, what's our result? 3. Now, when we look at f inverse, we say, oh, the output of f is 2. So we scan here for 2. Say, oh, well, there's a 2 right there. What was the input that made it? And we see, oh, it's at 1. So that says f inverse of 2 is 1. All right? Can you see the difference? So here, when we just ask for f of 2, says input is 2. So we say find where the input is 2 and check for the value for f. F inverse, output is 2. So we say, okay, where do we have an output of 2? And what was the corresponding input? All right, good, good. Not so bad. That's great. Well, let's hope they're all this easy. Okay, well, let's go to part B. Find f of 3 and f inverse of 3. Oh, this is turning into like an onion problem. Layers. Layers are fun. Okay, so let's start peeling our onion. F of 3. And we're going to start from the inside. And it says, okay, f of 3. So we come here, f, and input 3. F of 3 is 4. Right? So that's the same as f of 4. So, okay, f of 4 is 5. All right, good, good. Okay, f inverse, whoops, f inverse of 3. Okay, so we come along. We say, all right, where is 3? Well, right there. Our output is 3. So our output is 3 at 2. So this is the same as f inverse of 2. What's f inverse of 2? Well, if we believe part A, it's 1. Right? But again, where's the output to at 1? All right, that's not bad. Great, halfway done. Part C. G of x is f inverse of x squared cubed. Find g of 2. All right, so we have g of 2. So let's plug that in. That's f inverse 2 squared and cubed. So that's f inverse of 4 cubed. So we say, okay, come along. Where does f have output 4? Has output 4 at 3. So we say, oh, well, that's 3 cubed. And 3 cubed is 27. All right, good. Wow, we're doing great. One more. Here we go, part D. H of x is f inverse of x. Find h prime of 5. Okay, so let's remind ourselves here, how do we take a derivative? Because really what's happening is h is the inverse, and so we're asking how do you take the derivative of an inverse? So what's the rule? So we can say, look, h prime of x, that's our derivative of f inverse of x. All right, that's just what it is. I haven't used anything fancy yet. Okay, so according to the rules for derivatives of inverses, that's 1 over the derivative, and that's almost it. And there's just a little tiny tweak. And what's the little tiny tweak? Here we put f inverse of x. Okay, so there we go. That's our basic rule. Okay, so now that we know that, we say, all right, we're going to plug in 5. So what do we have? We have h prime of 5. That's 1 over f prime of f inverse of 5. Okay, so we say, okay, f inverse of 5. We come to our table, we say, where is the output 5? Because we're looking at the inverse of, and there's 5, and the output is 5 when we put in 4. So f inverse of 5 is 4. So this is equal to 1 over f prime of 4. Okay, now we go back to our table. Well, we know 4. What is f prime of 4? Well, it's 7, right? Because we can read our table. F prime of 4 is 7. So this becomes equal to 1 over 7. And I'll put a box on this one just because we did a little bit more work, but there's the idea. And that's it. We're done. So most of this problem was, can we read a table? And then, of course, a little bit of like, do we know the rules for derivatives of inverses? And of course, we study. We're good students. We're going to get those points. We're going to get all those points. Let's do it! Number 4. Find xy coordinates of all points on the graph of 8x squared minus 2xy plus y squared equals 224, where the derivative is equal to 0. Now, you don't need to know this. You might say, well, what does this look like? It kind of looks like a tilted ellipse. And that's because it's a tilted ellipse. But that's beside the point. Okay, so what are we going to do? What's going on with this problem? Well, notice it's not asking for x values because we don't really have y as a function of x. We have a relationship between y and x. So what's the situation? Well, this is an implicit relationship, right? So this is, when you have a formula involving y and x, we see that, we don't have y as a function of x, but y depends on x, and so this is an implicit function. So we're like, oh, and we're after a derivative. So, implicit differentiation, that's where we're at. Now, how do we do implicit differentiation? And the answer is, we have an idea. So let's recall what our idea is. So we look at this and we're like, and our idea is like, what we're going to do is say, look, I don't know what y is as a function of x, but I'm going to think of it as a function of x. That's how we're going to solve this. Okay, so let me write it out in sort of the long way about what that means in terms of our idea. We normally don't write this all out, but I want to sort of emphasize what's going on. So what we really have is we have 8x squared minus 2xy, which I'm going to think of as a function of x, and then plus y, which I'm going to think of as a function of x squared. And now we're going to take the derivative of both sides with respect to x. Okay? So here we go. Derivative of 8x squared is 16x. Here, when we take the derivative, what do we need? Product rule, right? Because x shows up in two places, both x and y. Now that's the key to this. You have to remember product rule. All right, so 16x, well, then here, derivative of the first, so that would be just 1. So minus 2, don't forget about that, minus 2 y of x. And then derivative of the second. Derivative of y is y prime, or dy dx. And say, okay, so that would be minus 2x y prime of x. Okay, here, what rule? Chain rule. Okay, so the 2 comes down, y of x to the first, and then times derivative of y of x, which is y prime of x. And then on the other side, don't forget, you have to take derivative of both sides when we're talking implicit differentiation. Well, the derivative of 224 is 0. And how do we know that? Well, it's a constant. But wait, it's a big constant. But yeah, big constants are still constants. And so we get 0. Nice. Okay, now that's it in sort of long form. Usually we don't write this all out. Usually we would just say the following. Oh, 16x minus 2y minus 2x y prime, which we can write as dy dx, and then plus 2y, and y prime is another dy dx equals 0. Oftentimes this will be the first thing you write down, because all the rest of this is happening up here. The power of your mind. All right. Now, are we done? No. But we're getting a lot closer. Okay, what do we know? Well, we're after points on this graph where the derivative is 0. So we're like, oh, we want the derivative to equal 0, you say. Well, that's cool. So what we'll do is everywhere where we see dy dx, we're going to put 0. All right, so great news for us. So we have that these parts are equal to 0. And so we have the conclusion that 16x minus 2y equals 0. Or we could say, hey, I can move over things around. That says y equals 8x. Now that's not our answer. But it tells us a relationship between x and y. And now we say, well, we have one relationship. We just found it. But there's two variables. Is there another relationship? Yeah, this one. The one that we started with. So we're going to take our y equals 8x and plug it into here. And what would that give us? Well, that would give us 8x squared minus 2xy, which we put in 8x, plus 8x squared, right? Y squared equals 224. Well, let's see, what does that give us? Well, it gives us 8x squared minus 16x squared. 2 times 8 is 16, plus, a big number, 64x squared. All right, now, if we've lived a good, clean algebra life, what should happen? Well, nice things. Because remember, our teachers love us. They want us to get the answer. They don't want us to not get the answer. All right, well, let's see what happens. 8 subtract 16 would be negative 8. 64 subtract 8 would be 56. And notice I'm just looking at the numbers because all of them have x squareds. So that's 56x squared equals 224. Now, does 56 divide into 224? It does. See, because our teachers love us. You know, you should expect lots of loves and warm feelings from your teacher as you're taking these tests. 224 divided by 56 is 4. Now, if you don't quite believe that right away, think of it as 4 times 50 would be 200, and 4 times 6 would be 24, and 200 plus 24 is 224. All right, good. Okay, so that's x squared. Well, if that's x squared, what is x? Well, that means x is either plus or minus the square root of 4, or x is plus or minus 2. So that says we have two x values. And we have this other relationship which gives our y. So we have 2 or minus 2 for x. And for y, well, 2 times 8 is 16. Negative 2 times 8, negative 16. And that says there are two places on this curve where we have a flat tangent line. So cool. Nice. Ah, what a lovely, lovely thing. All right. Well, let's keep going. Number 5. A child blows a balloon, which is assumed to have a perfectly spherical shape. Ah, what a mathematical thing to say. It's perfectly spherical. Ah, it's almost like physics saying, there's no friction. But all right, whatever. The surface area of the sphere increases at a rate of 12 pi square inches per second. How fast is the radius of the balloon changing when it reaches 3 inches? Okay, all right, cool. So let's think about what we have. Well, we're talking about rates because we're talking about, how fast is the surface area increasing? How fast is the radius increasing? So we have multiple rates, right? Can you see that we have multiple rates? The surface area increases. How fast? That's a rate. It's the radius. So whenever you see multiple rates, what's the type of problem we have? Related rates. So this is related rates. All right, cool. So now we know what type of situation we're in. We're in a related rates scenario. All right. Now, how do we approach a related rates problem? Well, we do it by saying, let's find the relationship. Well, what are the things that we want to relate to one another? So we say, okay, well, we have a surface area of the sphere. That's one rate that we talked about, because that's the rate. And then the other rate is the radius. So we're seeking a formula, ideally one formula which would relate those two quantities. So do we know what the surface area of a sphere is in terms of the radius of the sphere? Yeah, they told us. It's right here. Surface area is 4 pi r squared. So we can say we'll start with surface area equals 4 pi r squared. So I'm using SA for surface area. It's not S times A, it's SA. All right. Now, here's our beautiful thing. We're going to think of both surface area and our radius as functions of t. So they're not really, I'm not thinking of them so much as functions of each other, which it is true, but I'm going to think of like saying, well, surface area is a function of time, and radius is a function of time. So this is, again, what's going on upstairs. Lots of room up there. And so in particular, if we were to write that down, we would say, okay, our surface area as a function of time is 4 pi r of t as a function of time. We usually don't write it down, but if we were, that's what it would be. And now we're going to take the derivative of both sides with respect to t. Okay, so here we go. Derivative of the left-hand side, and I'll go ahead and just use prime notation for a second. SA prime of t. 4 pi is a constant. The 2 comes down. We have r of t to the first power times the derivative of r of t, which is r prime of t. Now, of course, my 1s and primes looks very similar. Maybe I should work on that. R of t to the 1, r prime of t. There we go. Or, if you like, that's really 8 pi r of t, r prime of t. Now, let's write this in a slightly different way. So let's suppress the of t. And if we did that, we would write that in this way. Namely, here we have the derivative of surface area with respect to time is equal to 8 pi. And we have r and dr dt. All right. So we normally will go straight from this step to that step. I'm just emphasizing this so we could say, what's going on upstairs? And so don't be like, oh, do I have to write all this out? No, no. Go from here to there. Boom, boom. You know, get it done quickly. I'm just going slowly because I want to make sure I'm highlighting all the ideas. Okay, so now we're going to go through and say, what do we know? Do we know how fast the surface area is changing? Well, yes, it's increasing. Pay attention to words. Increasing means plus, decreasing means minus. So sometimes they like to hide a little minus there by using the word decrease, but increase means positive. Good. So increasing at a rate of 12 pi. Okay, so increasing, it's plus 12 pi. Now, 8 pi, well, that's 8 pi. Cool. Do we know what r is? Well, how fast is the radius of the balloon growing when it, now here, this it, that's doing a lot of work. What is it? Well, it is the radius. So the radius is also 3. And how fast is it? Well, we don't know, but that's okay. That's what we're trying to find out. And so we have 12 pi is 8 pi times 3 times this rate. And this rate is what we're trying to solve for. So we say, okay, move things around. dr dt, what do we have? Well, we have 8 pi times 3. We have 12 pi. So we have 12 pi. 8 pi times 3, that's 24 pi. And the pi's cancel. 12 over 24 is 1/2. All right. Now that's actually the answer if we didn't care about units. And I don't know if we have to care about units. You know, it's one of those things where it's like, sometimes they'll explicitly state include units. Sometimes they won't. And then it'll take off points. Those pesky physicists always wanting units. So let's, in the spirit of caution, throw in units. Now, we could go back and try to figure everything out, but it's easier just to say, okay, what is radius being measured in? It's being measured in inches. And so it would be r, units of r is inches. What's time being measured in? It's being measured in seconds, right? Because we see this rate was 12 inches squared per second. So it's going up at 1/2 in inches per second. And there we go. There we go. Ah, what a lovely answer. All right, great. Now, not that they would ever do this to you, and I hope they never do. That's the physics thing, what I'm about to say, is we should have double checked to say, okay, were we always consistent? Was it always inches and inches? Sometimes people like to be a little bit devious and be like, oh, I'm going to make it inches here, but feet there. That's not how calculus rolls. We are the gentle, loving type. So, all right, well, that's it. Number 5. Let's keep going. Number 6. Let f of x be a continuous and differentiable function, also known as nice. And it's on the interval from -4 to +7. The graph of the derivative f prime of x is given below. So they really are emphasizing this is not the function. It's the derivative. How do we know it? Because it says it here in bold. Whenever they bold something, it's like, yeah, make sure you pay attention. It even says it here, f prime of x. Okay, so we're going to determine the following, and there's something here we have to be a little bit careful of, which is this phrase, justify your answer. So why are these things true? We want to make sure we can explain Not just say, oh, it's this way, but it's this way because of this. And we're not looking for long essays, short explanations. All right, let's start with A. At which values of x does f of x have an inflection point? Okay, so what do we look for? Well, when do we have an inflection point? Well, inflection point, this is concavity changes. Yes? Now, but be careful here. You might say, oh, I see there's an inflection point here and an inflection point here because, concave, concave. No. Remember, this is the graph of the derivative. So let's talk in terms of derivative. So there's another way to think about concavity changing. So where we say, look, f prime of x positive, well, that's concave up. F prime of x negative, f double prime of x, f double prime of x positive, I have to be careful here, concave up. F double prime of x negative, that says we're concave down. So we can look at this and say, all right, let's look at our picture. This is f prime. So in this range here, notice how f prime is going down. So we can say f double prime of x is negative for negative 4 less than x less than negative 2 because we're decreasing. As the derivative decreases, that says the concavity is negative. And then we say, oh, we see from negative 2 to positive 3, our derivative is increasing. So that says the derivative of the derivative, which is the second derivative, is positive. And that's between negative 2 and positive 3. And, well, okay, we keep going. And, okay, see how the derivative goes down? That says our second derivative is negative. So wherever the derivative is going up, second derivative is positive. Wherever the derivative is going down, second derivative is negative. So f double prime of x, my pen is trying to look weird on me, is less than 0. And that's for 3 less than x less than 6. And then finally we see our derivative is going up. That means the second derivative is positive. For 6 less than x less than 7. Okay, all of this put together, what's our conclusion? Well, our conclusion is our inflection points are going to be where we switch signs. So here are our inflection points. So we have inflection points at x equals negative 2, at positive 3, and at 6. Okay, there we go. Now there's a couple other ways you could say this. You could say, well, when you're looking for inflection points, you're looking for maxes and mins. So where you see a min or a max for the derivative, that's an inflection point. And then we say, oh, well, we can see where the maxes and mins are. They're at negative 2, 3, and 6. So mins and maxes on the derivative correspond to inflection points. All right. Well, part B. On which intervals is f of x concave up? Okay. We've actually answered this as we talked about part A, because we talked about concavity. And we say, okay, well, concave up, this equals f double prime of x being positive. And so we say, well, so the intervals are negative 2 less than x less than 3, and 6 less than x less than 7. Okay, so great. Second derivative is positive. In other words, where we're increasing, we're concave up. All right, on which intervals is the function concave down? Well, again, concave down. And that's when the second derivative is negative. And we already noted this in part A. Like, well, this makes it easy for us. Part A did all the work. Okay, so when are we concave down? Negative 4 less than x less than negative 2. And 3 less than x less than 6. And there we go. So the justification, we're looking for things like concave up means what? Concave down means what? And so what is it you're really looking for? Inflection points are what? Well, we can really say inflection points are where we change signs. And I'll be honest with you, knowing what to say and justify your answers can be tricky. But yeah, I don't need to say too much. Maybe we should add inflection points since f double prime changes sign. That's good. There we go. There we go. Now you might say, should these be open intervals or closed intervals? And that's an interesting discussion. And I go on one side of it, and I know some of the faculty go on the other side that I have. So let's just say yes. You'll be fine. They're not going to go into that fine a detail. Okay, there we go. Whew. All right. Well, there's just one more. Let's take a look. Number 7. We made it to the end. But let's finish it up. All right, what do we have? Suppose that y equals f of x is a differentiable function from negative infinity to infinity. Okay, so it's nice everywhere. And it satisfies the following. The derivative at 0 is 0. The derivative is less than 0 if x is less than 0. And the derivative is greater than 0 if x is greater than 0. Okay, well that's interesting. And okay, define g of x is f of x squared minus 1. Determine all intervals on which g is increasing. As always, give reasons for your answer. I don't know if it's as always, but okay, all right, all right. Well, this is going to be interesting. Okay, so let's dig into this. So what do we have? Well, let's start by saying what's g prime of x, right? Because we're after intervals where it's increasing, so that's the same as saying when is g prime of x greater than 0? Okay, so that was our first observation, is how do we translate this requirement? Okay, so let's talk about g prime of x. So g prime of x, well, that is chain rule f prime of x squared minus 1 times the derivative of the inside, which is 2x. All right, well, now things get they get interesting. Because well, what do we know? We know 2x can change signs. And we know f prime can also change signs. Well, let's figure out all the places things could change signs. In other words, first off, let's find our zeros. So suppose I say this equals 0. Let's find that first. Well, okay. Well, we have a couple of options. One could be that this part equals 0. And all right, well, that's easy to spot. Okay, actually, that was really easy to spot. X equals 0. The other thing is that says, hey, what about this part? F prime of x squared minus 1. F prime of x squared minus 1 equals 0. When is the derivative equal to 0? At only one place, right? Because it's either negative if x is negative. Well, let's be careful here. It's negative if the input's negative. It's positive if the input's positive. And it's 0 if the input's 0. So that says, oh, that happens at x squared minus 1 equals 0, the input being 0. And that's the same as saying x squared equals 1 or x equals plus or minus 1. Okay, so right now, let's summarize what we've just said. So g prime of x equals 0 at x equals 0, 1, negative 1. Why is this helpful? Well, now that I know those are the 3 points where it equals 0, then what I can say is, hey, this really takes all the numbers and we're splitting them up into a few pieces. 4 pieces in particular. We say, all right, let's think about what happens on each piece. So pick a number bigger than 1. It's 2. Yes, 2 is bigger than 1. Thank you, Steve. Okay, all right, so let's say, what is g prime of 2? Well, according to this, that would be f prime of 3 times 4. What do we know about f prime of 3? Well, we know f prime of 3 is positive because the input's positive. So this is greater than 0. Okay, so g prime here is greater than 0. Okay, how about between 0 and a half? Hey, I have one for you. A half. All right, yeah. So g prime of a half. What happens? Well, that would be f prime of 1/2 squared minus 1 is negative 3 quarters, right? Because a half squared is a quarter, minus 1 is negative 3 quarters. 2 times a half is negative 1. Now, plug in negative 3 quarters. Since it's negative, the derivative is negative. Negative, negative makes this a what? Oh, wait. 2 times a half. This is plus 1. I was thinking of, I was already getting ahead of myself. That's negative, that's positive. Negative positive says this is negative. Okay. Whew. Sorry about that. All right. How about here? Well, again, we'll plug in g prime minus a half. Now when we plug this in, this is f prime of minus 3 quarters times minus 1. There we get the minus 1. So again, f prime of minus 3 quarters, negative number, negative derivative. Negative, negative makes a positive. This is negative. So that says g prime is positive. And okay, coming over here, and we'll plug in negative 2. And what is that? Well, that's f prime of 3 times negative 4. But f prime of 3, because 3 is positive, is positive. Positive times negative makes the whole thing negative. So g prime is negative. All right, so we plugged it in. We found the zeros. We said, okay, so now that we know the zeros, those are our critical points. And now let's test each interval. So we tested each interval. And our classic, it alternates sign, and that tends to happen a lot. And so now our conclusion is we can read it off. So where are we increasing? Well, we look for where our derivatives are positive, right? And we see 2 places. So our intervals are from negative 1 less than x less than 0. That's this interval. And 1 less than x less than infinity. Now, again, you might say, well, should this be less than or equal to? You would have some very interesting arguments from your math faculty, but let's just say we're done. And we are done. So those are the right intervals. All right, good. That one was interesting. Well, sometimes I like to throw interesting problems our way. And so it's good to see one now and then. And may all your exam problems not be that interesting, right? Okay. Well, thank you for joining me. I hope this helps, and I hope you do great. You're wonderful. I believe in you. Have a great day. And maybe I'll see you again. Bye.